The purpose of this lesson is to learn database design basics, keywords, database diagram and notation types, diagramming programs and websites, cardinality, normalization, and normal forms. Database design can be broken into two major parts. You have logical design and physical design. In logical design, we're actually designing the database on paper or in some sort of designing program where we don't worry about what the actual requirements and constraints are of the DBMS that we're using. It's the first step in creating a database. Once we have our logical design finalized and we know what DBMS we're going to be using, then we can actually do our physical design. And the physical design is when I know what DBMS I'm using, then I need to figure out what the exact constraints, data types, security features, all of that kind of stuff that the system actually supports. And then I actually type my design into the DBMS. That's the physical design. Some of the keywords that you need to know, there is what's called a schema, and the schema is everything that makes up the database. That includes our tables, views, roles, permissions, indexes, and etc. We have entities, which are our tables, and remember tables have columns, which are called attributes, and they have rows that are called tuples. The row is also called a record. And every record has to have a primary key. A primary key is an attribute that uniquely identifies the record. Now, in certain instances, I may have more than one column that could possibly be the primary key. And in that case, all of the columns that could be the primary key are called candidate keys. So what will happen is if I have 4 or 5 columns that could be the primary key, then those 4 or 5 columns are candidate keys, and I have to pick one to be the primary key. The ones that I did not pick are called alternate keys or secondary keys. They're just simply the ones that I didn't pick to be the primary key. We also have foreign keys, which a foreign key would be an attribute that forms a relationship. So that would be a attribute where I have to go and do a lookup in somewhere else in the database to be able to figure out what that particular piece of information is for. It provides a link between tables that forms our relationship for our relational database system. We can have a composite key, which is just simply 2 or more attributes that comprise the primary key. We'll get into those more in a little bit. We need to worry about what's called referential integrity. Okay, so this diagram is an example of what's called an entity relationship diagram, or ERD. There are all sorts of versions of these things, so we'll cover a couple of them. In this version, we have a customer table, or order line, product, and the customer table has an attribute called customer ID that is the primary key, and notice it's underlined. And then we have these other attributes for the person's name, address, city, state, and so forth. All right, so for each customer that's out there, they have all this information. And then for every order that we have, notice there's an order ID. So an order ID was placed on a certain date by a particular customer. And you'll notice that order ID has the underline, so that's also our primary key. And then customer ID has the dotted underline. Now this means that this is a foreign key. And what that would mean is that order ID number 20 was placed on a certain date by customer ID number 15. Okay, so who is customer number 15? Well, we have to go and look that up. Okay, customer number 15 is Bob Smith. He lives at a certain address. That's called a foreign key. This is our actual basis for a relationship. Now, in referential integrity, it says that if I use customer ID number 15 here in the order table, it's going to go do and try a lookup, and it has to find customer number 15 in the customer table. If it doesn't, it won't let you write customer number 15 to here. Referential integrity says that wherever I reference something somewhere else, it better exist. Okay, so database diagrams, there are many different types. The first one that most people see is what's called a Venn diagram. It's this one up here. And the way that this works is we have each table name, just the name of the table, goes in the rectangles. And in the middle here is our relationship between the two tables. So in this case, I have for each person, there is a location. So I could say that each person has a birthplace, which is a location somewhere. And what you'll see a lot of times is this item in the middle here is a relationship, and it will be a verb. So we'll see a noun, verb, noun. The next one is the one that we're going to be using throughout the lessons today. It's called IDE F1X, and it shows the database tables like this, but then it will also show all of the attributes listed underneath of it. The next one that you'll typically see is going to be crow's foot notation. Now, you'll see today we'll actually use crow's foot and this format to actually combine together and make different types of ERDs. And then the last one that you'll see a lot of times is this UML. And UML is the Universal Modeling Language. It is used for modeling object-oriented programs and databases. So an ERD is just simply a graphical representation of a database. And in most of our versions, you will see that the entity name or the table name is listed at the top. The left column over here is used to list which of the columns have special characteristics, like are they a primary key, foreign key, are they an index. Those are listed on the left side, and then all of our attributes are listed on the right. Now in this particular version, the way that it works is our primary keys and foreign keys are listed in the top, and then all of the other attributes are listed in the bottom section. Like I said, there are other variations that exist. These lines with the arrows, they show relationships between the tables and which way a lookup would have to go. So we're going to use different programs to be able to make these diagrams. The industry standard is Microsoft Visio. It is an expensive program because you have to purchase a copy of it for each computer on which you want to use it. So if you're going to use it at school and at home and a friend's house, you have to have a copy for each of those computers. But it is the industry standard for designing diagrams. Now, if you are looking for a free one, there's one called Dia. Dia works on Windows, Linux, Mac OS X. It is free, but once again, it has to be installed on each computer. So we'll show you what these look like in just a second. So this is Microsoft Visio. Visio, once again, is the de facto standard. And in this case, there is a sample database that they include called AdventureWorks. And AdventureWorks, what they've done is they've listed all of the entities for their database, and then they've color-coded what their purpose is or what department that they belong to. So if I zoom out, you will see that all of our entities and all of our attributes and all the other stuff are listed here, and then they've color-coded it so we can tell what department these belong to. So if I were to look at this particular item, I didn't mean to move it, I want to scoot. Alright, so I'm going to zoom in here. I will see that this is an entity called Sales Order Header, and it has a primary key of Sales Order ID. It has all of these attributes. I can tell you that these are foreign keys, the ones that begin with FK. The U's, these are indexes, which we'll discuss that more in detail later. But I can look at this and see that these are all of our attributes, and then I can follow the lines to see where they actually reference somewhere else. So I can see the relationships between the tables in a graphical manner. This one is Dia. Now, Dia, once again, is free. It was originally a Linux project. It's not quite as pretty as Visio is, but it does everything that Visio will do. It just is not as well known, and it's not as well maintained, and they don't have a marketing department behind it to make it look pretty. But it is a free program that will do all the same kind of stuff that you're looking to do with these diagrams. Now, instead of using a desktop program to make these diagrams, I'm actually going to be using a website called Lucidchart. It is free for small projects and educational purposes, and if you are a college or university student, you can get a free educational upgrade. Essentially, you get the full program for free the entire time that you're a student. You have to actually do a search for the educational discount, but once you do that, you have access to all of the features that it has. You can use it from anywhere. It is a website, so you actually save the diagrams on their server. So if you make a diagram at school and then you go home, or you make it at a friend's house, you actually have access to it from anywhere, and you can continue working on it without having to reinstall the program somewhere else. It does allow you to upload and download Visio files. So if I have Visio on a computer at home and I'm making a diagram at school, I can save it, go home, download it, work on it in Visio, and then re-upload it back to their website. So it will actually allow me to import and export most of the common formats. It also does allow me to use Visio stencils. So if I have a stencil, which a stencil is just simply a file that has pictorial representations of different products that are out there, like networking equipment and computers, I can actually upload those to Lucidchart. My favorite feature, though, is that it has built-in collaboration. If you and a couple of other people are working on the same diagram, you actually can be in the chart editing it at the exact same time that other people are working on it. And I'll show you what this one looks like. Alright, so this one is Lucidchart, and Lucidchart is a direct Visio competitor. They actually will position themselves in the same market space as Visio, and like I said, it's completely free for small projects. Now, one of the things that you will have to do when you first sign into it is you will have to turn on these entity relationship diagrams, and those are located down here under More Shapes. So anything that you are going to be using, you just simply need to select it here and then save it. Alright, so what I have done is I created a diagram here in Lucidchart. It has an entity called student, has a primary key called student ID. Here are the other attributes. I have an entity called class, has a primary key of class ID, and here's a foreign key called building ID, which means that points somewhere else. So that means I have to look in another table. And you can see here by this line that I've actually formed a relationship between the tables, so I can see where the foreign key points. We will actually get more into this type of diagram here in just a minute. Before we get into designing the ERDs, we need to talk about other ways to represent a database. Remember, we talked about the logical design is where I write it down on a piece of paper. Well, I can draw it all out as ERD diagrams, and I can draw every single relationship, or I can do what's called a shorthand representation. And shorthand is actually a text-based representation. So the way that this works is I'm going to list the entity name, remember that is the table name first, open a set of parentheses and list all of the attributes inside. And the primary key would actually get an underline. And then if there is a foreign key, it would be a dotted underline like this. Okay, now the catch with this standard notation is I don't really state where this goes to. So I am assuming, based on the four tables that I have here, the building ID is a foreign key, and it probably points to building ID down here under the building table. But there's really no way to specify in this where it goes. I'll show you another one in a few minutes that actually will allow you to do that, though. But the one that I want you to pay attention to is this one right here where it says student class. We have student ID and class ID. And if you notice, both of these are underlined. That means that they are both the primary key. This is called a composite key, and this table is actually designed to link two other tables together. We'll get to that one in just a minute. So the other way that I can represent it is what's called database design language, and this is called DBDL. It's a more detailed textual database representation. So it works just like standard notation, but we don't use underlines. Instead, we list things underneath. So I have my primary key is listed as a PK here, and so for this particular table called student, PK, our primary key, is student ID. And then I have an alternate key called email, so I could have used that one as our primary key, but I chose not to. Alright, so our class table, we have a primary key of class ID, and then we have a foreign key called building ID, and in this case we use this arrow to point where it goes to. So we tell it, hey, this building ID foreign key points to the building table. You notice this is all caps, so that's the name of a table down here. So if I were coming into this table and I look at this, I say class is this and the building ID is 3, I'd have to go to the building table and look at building 3 and see where it actually is. Here we have student class. This is the one that had the two primary keys, so it had the composite key. We simply list PK and then the first one, so student ID, comma, and then the second one. They're both listed right on one row. We also have to worry about this thing called cardinality, and cardinality is just simply stating how are database tables related. So how many of a particular item in one table can be related to how many of a particular item in another table. So I could have something like, I could have a database with with songs and artists, and I could say that many different artists make many different songs. Or I could have a list of artists and album covers and things of that nature. So we can state how many each of those can have. All right, so we have three options. We have a one-to-one relationship, we have a one-to-many relationship, and we have a many-to-many relationship. We do not ever want to use the many-to-many relationship if we can help it. We'll get into what that means, but an example of it is going to be students and classes. I could say many students can take many classes. And if I can do that, if I can say that many students can take many classes, I have a many-to-many relationship, which means that I don't want that. I need to break that up somehow. So what I'm actually going to do is I'm going to introduce a third table as a way to link those together. We can use crow's foot notation, which this is a way of replacing the arrows at the end of the lines to show what the cardinality is. So if I use these different symbols, this one means that I could have anywhere from 0 to 1 of this item that's in this table. This one means I could have anywhere from 1 to 1. So in other words, it's exactly 1. I could have anywhere from 0 to many. This one means many. So it's either 0 or many. And then this one here is I either have 1 or many. So I have at least one of these items, if not many of them, exist in this table. We'll get into those here in a little bit. What we need to worry about when we're designing our database is this process called normalization. It's a process of progressively modifying our tables to make them where they are more efficient. We can reduce redundancy, and also we can reduce possible problems. One of the other things that normalization will do is it will prevent us from creating artificial limitations on the data that's in the database table. The main thing we're trying to avoid is what's called an update anomaly. We really want to prevent those, because what happens is we'll design the database, and then when we're done designing it, we may forget that certain things are made a certain way. When somebody tries to insert something into the database, and they may make a record that actually breaks our relationship, and those are called update anomalies, and we don't want that to happen. Now the thing is when we do this normalization process, we usually end up with smaller database tables, but we end up with more of them. The thing is the more normalized I make it, the less possible problems I have, but the more processing power that my database will actually require to run well. So our normal forms are first, second, third, and fourth normal form, and we represent these as 1NF, 2NF, 3NF, and 4NF. So first normal form, and one thing you need to remember with these before we get into first normal form, is actually that we are in the process of progressively making it better. So first normal form is your first step. Second normal form is going to be that I've done all the stuff for first normal form and some extra stuff. Third normal form is going to be I did all the stuff for first normal form, I did all the stuff for second normal form, and now I'm going to do some extra stuff, and so forth. Okay, so first normal form says that all the records must have the same number of attributes. So if I have some records, so one of our rows, it has to have the same number of columns as every other row that's in that same database table. We can also have no repeating values. So what this means, in this example, I have a table called pet owner, and each pet owner has an ID and a name, and then we list in the table pet 1, pet 2, pet 3, pet 4, pet 5. And if I were to list it in this manner, what happens is I create an artificial limit. And my limit is that owners cannot have any more than 5 pets. So how do I handle it? Okay, I have somebody comes in and they have 7 pets. Well, then I'm going to have to create 2 more columns called pet 6, pet 7, and so forth. And I'm going to keep doing that. And then I have somebody who comes in with 30 pets and 100 pets and 200 pets. And well, how many am I going to actually put in there? So no matter what, I'm going to have some sort of limitation on how many pets somebody can have. So by doing it in this manner, I'm actually creating an artificial limit. So first normal form just simply says that we can't have this. Alright, so what happens is it's a waste of space, because let's say I have a person that comes in and they only have 1 pet. Well, even though I'm going to enter empty values into those other columns, it actually does end up wasting space, because the system will allocate memory for each record and each attribute. So even though they're empty, what's called a null value, and a null value just simply means nothing was entered, it still wastes space. Okay, so second normal form says that we have a primary key defined. And the primary key is a unique value. So for each employee that we have in this example, they have an ID, and every employee is going to have a different ID. Now, the primary key can comprise more than one column, that's okay, but the primary key has to determine all of the other attributes. So what this means is that if I were to tell you employee ID number 3, you would be able to look and see their name, you'd be able to see their address, you'd be able to see their manager ID, their manager's name, and their manager's title. You could tell me that just by simply looking at the record for employee ID number 3. Alright, so it does meet second normal form. But the one that it does not meet here in this example is what's called third normal form. Now, third normal form is that all of the non-key attributes, all the non-key columns, have to depend on the primary key and not on other non-key attributes. Alright, so what does that mean? Alright, so that means second normal form, if I were to tell you employee ID number 3, you could tell me their name, address, manager's ID, the manager name, and the manager's title. But if you go the other direction, if I look at every one of these other non-key attributes, okay, the name for this person depends on their ID. I can see that. Their address depends on their ID. The manager's ID, that would depend on the employee ID, maybe. But the manager's name doesn't have anything to do with any of the stuff that has to do with the employee. The manager's name depends on the manager's ID. The manager's title depends on the manager's ID. So what happens now is this database table is in second normal form, but it's not in third normal form. And third normal form is where we're actually trying to get to. That is our ideal, that's the normal form that we want. So how would we fix it? All right, well, to fix it, we break it apart into multiple tables. So what you will see here is that this right here should be one table. This right here should be a table, and then we need something to link them together. Okay, so what I did was I created a table called employee, and it has the employee's ID, the name, and the address, and the primary key of employee ID. I have a manager table, which has a primary key of manager ID and the name and the title for each of those. And then I created a table that is the combination of these two table names. So I have employee underscore manager. And you will notice that in this table, I have employee ID, comma, manager ID. Now, what happens if I were to make the employee ID the primary key? All right, what that would mean is that I could only ever have one employee ID, and I might have an employee that has more than one manager, and that wouldn't work. All right, so if I want to make the manager ID the primary key, well, what that would mean is for that to be unique, I could only ever have each manager's ID listed once. That won't work. So what I did in this one is I make these two a composite key. So this table is designed to link these two tables together. Therefore, I take the primary key out of each of these and use both of those to make a composite key. And then they're also a foreign key. So the employee ID here is a foreign key that points back to the employee table. So if I were to say employee ID number 3 has manager ID number 20, then I'd say, okay, well, employee ID number 3 is this person that says Bob Smith, and his manager is 20, so I go back here and I see that that's Jane Doe. So I am actually going to use these as the primary keys and as the foreign keys. All right, so here's an example. Our local college is trying to keep track of all of the students that they have enrolled, and they've been doing this in a spreadsheet. And the spreadsheet is becoming inefficient. It breaks easily. And so what they were doing is they were storing every single student in one row. So if I were to look at row 1, and I would see student ID number 20 is Bob Smith. He took class 1, class 2, class 3, class 4, class 5, and so forth, and they list all of his classes. Well, we're back to that first normal form where we have that artificial limit because we have those repeating values. All right, so what I need to do is I need to figure out some sort of way to implement this. All right, so they designed it like this. They created a student table that has student ID, first name, last name, what program they're in, their email address, and then all of their classes are listed here. Now, what you'll notice is that each student is limited to only 3 classes. Now, if I want to have a 4th class, I'd have to create another attribute. If I have a student that has 20 classes, I have to have 20 attributes. All right, so what they did is they have class is our table that keeps track of what classes are offered. Each class has an ID. Each class have a name, what day it's offered, what building it's in, what time it begins, what time it ends. This table is okay, but this one is not. So what we need to do is we need to show something that is, how do we relate our students to our classes? And the way that we're going to do that is we're going to break this relationship here and move this stuff off into another database table. So here's how we would fix this. I'm going to take the 3 classes out of there, and the student table just strictly has information about the student. The class table strictly has information about the different classes that we offered. And if I want to make a relationship between the 2 of these, then I make a student underscore class. And remember, I said that you take the primary key from this one and the primary key from this one, make those the composite key, but they're also going to be foreign keys. So what I will see is down here, I'll see student ID number 20 is taking class number 3001. So I'd have to say, okay, well, who is student number 20? And I come up here and look, oh, student ID number 20 is Bob Smith. Class ID 3001, oh, well, let's go see what that is. 3001 is here, that is botany. So I can actually now do a lookup. Now what this does for me, though, is I can have an unlimited amount of classes for each student, or I can have students that don't have any classes and I don't waste any space because only people that actually have classes are going to be listed in this database table. Alright, so what I've done though is I've formed a relationship here by these lines. Alright, so the lines show that I have a relationship between student ID here and student ID number here. And what you will notice is I have, for each student that's here, each student could take anywhere from 0 to many classes. So I could see this person not listed in here at all, or I could see them listed in here many times. And then for each class that we have over here, it's possible that nobody took the class, or it's possible that a lot of people took the class. So I have a 1 to many relationship here, and I have a 1 to many relationship here. So now I have either a 1-to-1 or 1-to-many relationship that I need. I don't have any many-to-manys, and this is a better database design. Fourth normal form is our theoretical best form. However, in practice, it actually causes too many lookups and very slow response times. So what will happen a lot of times is people will overly normalize their database. They'll get into fourth normal form and then realize the system runs really slow. And so we have to do this process called denormalization, which means get it back into third normal form, so that way we can cause the system to speed up a little bit. Alright, so what fourth normal form says is that any record should not contain more than one related attribute. So what does that mean? Okay, so for this example, it says the employee table should not list the employee's personal information, mailing information, contact information, and salary information. Those should all be in separate tables. So what I should have is for each employee ID, I should only have one piece of information in each table. So in this case, I would have an employee info table. So that's their employee ID, first name, last name, birthday, social security number, and that's it. And then I have a table that deals with this employee's address. And then I have a table that deals with this employee's telephone number, the address table here, which apparently I repeated, and then their salary table. And they should all be separated out. Well, the problem is that we're going to have to do lookups that will actually cause the system to run really slow, because if I want to see what the address is for Bob Smith and what his salary is and get his telephone number and print that all out on one row, it would actually have to do 4 different lookups in 4 different tables, which would cause the system to run slower. So in this lesson, you learned about the database design basics, some of the keywords that you need to know for database design, the database diagram and notation types, some of the diagramming programs and websites, what cardinality is, and what normalization and the different